All right, here we're in section 4.3. We're looking at exponential functions. We're going to define what an exponential function is, as well as how to graph an exponential function. Okay. I've started with just a review of our laws or properties of exponents. Just doing so because some of these properties are going to show up within our different examples. Okay. Now, an exponential function is going to be any function of the form f of x or y equals a to the power of x. And we have a stipulation here on the value of a. It has to be a positive real number that isn't 1. So a can be any positive real number except for 1. And our domain for f, meaning any number that we plug in for x, it could be any real number. Okay. So I want to start off by graphing just a basic exponential function of f of x equals 2 to the power of x. I'm going to do so with a table of values. I'm going to plug in a couple positive values for x, as well as 0, and then a couple negative values. We know that 2 cubed is 8, right? So this graph is going to have the point of 3, 8 on it. 2 squared is 4. So 2, 4. 2 to the first is 2. So 1, 2. Anything raised to the 0 power is 1. And then 2 to the negative first power, here's where property comes into play. That's equivalent to 1 over 2 to the positive first power. So this is going to equal 1/2. So we have negative 1, 1/2. 2 to the negative second, using the same property, is going to lead me to 1/4. 2 to the negative third is going to lead me to 1/8. Then I think you can see the trend. 2 to the negative fourth would be 1/16. 2 to the negative fifth would be 1/32, and so on. Okay. And what we should be observing here is that our y values are never going to go negative. They're going to get infinitely close to 0, but they're never actually going to result in 0 or a negative value. Okay. So what we have here is what's known as a horizontal asymptote. The x-axis is a horizontal asymptote. Asymptotes are lines that your curve approaches but will never get there. They get infinitely close to it. Okay. Now this means that this function has no x-intercept. And then notice where the y-intercept's at. It's at y equals 1. And again, that's because anything raised to the 0 power would equal 1. Okay? All right, so at this point, I actually want you to pause the video, and I have a second exponential function for you to graph on your own on the practice 1 sheet. Use the same x values that I have in this example, so the numbers 3 through negative 3 when you make your table of values. Okay, so pause the video, take a few minutes to do that, and then come back and pick up with me. All right, so notice this function is just equal to 1/2 x. So here my a value is smaller than 1, okay? And what we want to notice is there's definitely some similarities between this function and the one that we did together in example 1, but there's also some differences, okay? So starting with the similarities, both graphs have an asymptote of the x-axis, and then both graphs have a y-intercept of 1, okay? Now, as far as differences, notice this function is decreasing as you move from left to right, whereas the previous function was increasing, okay? And that's just the difference in the a value, okay? Whenever a is larger than 1, you're going to have an increasing function, and whenever it's smaller than 1 but larger than 0, you're going to have a decreasing function, okay? So I put together a list of properties that include some of those observations that we just made. So for any function of the form f of x equals a to the power of x, we know the domain is going to be the set of all real numbers. We know the range is going to be the set of all positive real numbers, anything greater than 0. There will never be an x-intercept for a function of this form, and the y-intercept is always going to equal 1. Okay. To go along with that, that means the x-axis is always going to be your horizontal asymptote. And then these last two properties, this is kind of what we observed as the differences between our two examples. So as long as your a value is greater than 1, the graph's going to be increasing. Also notice it is 1 to 1. This would be an exponential growth situation. And then if your value for a is between 0 and 1, then your graph's going to be decreasing, but still 1 to 1. Okay. Now there's also a theorem that is pretty exclusive to an exponential function of this form. Okay. Notice that f of x plus 1, if you divide that by f of x, it's always going to equal the a value, the base of the function. So what we mean by that, if I go back to our first example, we're saying that if we take 2 points on the graph whose x-coordinates are 1 unit apart, so let's take here and here, okay? This point has a y value of 8, and this point has a y value of 4. If I take 8 and divide it by 4, I get the base of 2 that the function has. Similarly, if I took the y value of 4 and I divided it by a y value of 2, I get that base of 2 as well. Okay? All right, let's give you a proof to that also. And this would involve a property of exponents. So f of x plus 1 would be equivalent to a to the power of x plus 1. And f of x we know is equivalent to a to the power of x. Well, I can use the property of exponents here and subtract the exponent of the numerator by the exponent of the denominator. And notice that results in a to the first power. These will cancel out, which is really just a, right? So there's a nice quick proof. And this is just a way for you to identify whether points from a set are in fact representing an exponential function. Okay, that's what this theorem would be used for. All right, now let's take our functions and kind of make them a little more sophisticated, spruce them up a little bit. So here I want to graph f of x equals 2 to the power of x subtracted by 4. I'm going to do this using my transformation rules, thinking of y equals 2 to the power of x from example 1 as my parent function, okay? So what's happening in this function is that y equals 2 to the power of x is being translated down 4 units. That's all. All right, so if here's my original, I'll use the same critical points from example 1. I'm just going to shift each of those 4 units down. And understand that's going to move my asymptote as well, right? So let's draw in the asymptote. Now I'm going to be right there at y equals -4. And I would have my points in these locations. And there you have it. All right, second function there, f of x equals the negative of 2 to the power of negative x, has two transformations taking place, reflections across both the x and the y axis. Okay, so let's state that. Same parent function of y equals 2 to the power of x. All right, so one more time, I'll graph the original. Okay, and how about I do y equals 2 to the power of a negative x first. So that's going to give me a reflection across the y-axis, okay, which is changing the signs on all of my x coordinates from the original points. Notice the asymptote stays the same. Okay, and then I'll bring in the reflection across the x-axis now. So I take all of the points in red and change their y coordinates signs. And there we have our graph of f of x.